Okay, so welcome back. This is part 13 on our series where we show you how to program your bench test instruments like your signal generator and your oscilloscope. And we're using Visual Studio and C#. You can use whatever IDE and programming language you want. The concepts are all about the same. And we've shown you how to develop this application that we have so far. So what does this application do? Well, it started out, we showed you in the beginning episodes, how to control, using this software, how to control your signal generator and your oscilloscope. And the initial functionality we gave this application was to perform a frequency response analysis. So what is that? It basically allows you can see up here, you set your signal generator, every time step, you set your signal generator output voltage to a certain frequency, apply that to whatever circuit you want to test, and then measure the output of that circuit on your oscilloscope. So we're controlling the signal generator and the oscilloscope, and we did a frequency response analysis, which as you step through the range of frequencies coming out of the signal generator, it plotted the resulting oscilloscope voltage, and you will get a plot of frequency response of your circuit. After that, we looked at this additional functionality you see here, which is we gave the software the ability to grab waveforms as displayed on our oscilloscope. And you can see we have 2 channels worth of waveforms that are being updated every 0.2 of a second in real time. And we've got, in blue, we've got channel 1, and in red-orange, we've got channel 2. And you can see we can disable channel 2 and only show channel 1. And then we can disable channel 1 and only show channel 2 or show both of them. So now that we've got that, the next step we're going to do in this video is we're going to get some measurements for these waveforms, right? We want to know, like, what's the frequency? It'd be nice to be able to automatically calculate the frequency. As you can see, we've got up here on the top of the chart, we've got channel 1 frequency that we're measuring for this blue channel 1 waveform, and also the channel 1 peak-to-peak voltage, which is 7.04. And you can see the scale here, 0, 2, 4, 6, 8. And then the scale on channel 2 is 0, 1, 2, 3, 4. So we have to figure out how we're going to measure these values, frequency and peak to peak for both of these waveforms. There's a couple ways we can approach this. Now, as you recall, when we developed this application that grabs these waveforms and puts them to this chart, we have lists specifying all of these points for each waveform. So we've got voltage and time for every one of these, what turns out to be 1,200 points. If you think about it, since we've already got lists defining each point, voltage and time, we can go through those lists and calculate, for example, frequency. In a previous video where we developed software to measure frequency of the wall outlet using an Arduino, what we did is we measured frequency by looking at, as you can see here on the blue, the first positive going 0 crossing, and then we wait for the next positive going 0 crossing and figure out the time difference, and that gives us the period of one waveform, and then we can invert that to get the frequency. So that's an option. We can actually go through those lists point by point and measure frequency. And we can easily measure V peak to peak. We can do like a maximum, find maximum of all the values and then minimum of all the values, and that will give us the peak to peak. So we can do post-processing of these lists. That's an option. Now another option is we can ask the oscilloscope, because as you know, as we talked about before, the oscilloscope basically grabs millions of data points for each channel in each scan and has to filter those down to only 1,200 points to display it on these waveforms, because, you know, your oscilloscope screen has only, 800 by 400 pixels. So you can't put millions of data points on 800 pixels wide. So the scope grabs millions of pixels and filters those down to these relatively few pixels on the screen. Actually, the oscilloscope is making a lot more accurate measurements internally. Rather than us relying on just 1,200 data points, the scope is using a lot more accurate results. So what we can do is we can ask the oscilloscope, every time we grab a waveform, say, hey, by the way, what are your measurements of the frequency of that waveform? And what are your measurements of the peak-to-peak voltage? And actually, as we showed before in the programming manual for this oscilloscope, it does a lot of different types of measurements. It just does many, many measurements. So what we're going to do is we're going to ask the oscilloscope, after we grab each waveform on each channel, hey, what's the frequency? What's the V peak to peak? And then we're just going to grab those numbers and put them into these labels. Now, there's a couple things else we're going to have to do. We're first going to have to, as we did before, we're going to have to parse the numbers because, as you recall, all of the data coming from the scope is in byte format. It's got an array of bytes, and we have to convert those bytes into usable numbers. Now, the bytes represent scientific notation. So, for example, this kilohertz value, we're actually going to get it as 1e to the fourth, or 1 times 10 to the fourth, or 10,000 hertz. So we're going to have to parse them so that we get the correct value. And also, you can see up here, I have made it a little bit easier, more visually pleasing. If the value is a kilohertz value, I have added some logic to say, well, I'm not just going to put 10,000 hertz, I'm going to put 10 kilohertz. So I'm also going to add some logic to clean this up. And if it's in megahertz, I'm going to put megahertz. And if it's in hertz, I'm going to leave it as hertz. So we got some logic to do there. Keep in mind we're going to do that for both channels, depending on which channel is enabled. Now, another thing that's very important, as we mentioned before, if your waveform that you're measuring is clipped or there isn't enough information in the waveform on the scope, we're going to get bogus readings from the scope because it just can't measure. So let me give you an example of what that looks like. So now what I'm doing is I'm going to vary the magnitude of the channel 2, the triangle waveform on the scope, and watch what happens to the value. So it's up to 7, 8, 9, 10, 11, and you can see now the waveform is getting clipped. And if you look at the display up here on the chart, it's got asterisks because I've also added some logic to say, hey, if it's an incorrect reading from the scope because it's clipped, or what I'll do is I'll change the x-axis time scale, and you can see there isn't enough information to measure the channel 1 frequency. So the channel 1 frequency is going to be just shown as 0. So we are going to have to add some code for these bad readings. So now we know we're going to have to grab data from the scope. We're going to have some labels up here. And we're going to have to allow for bad readings for clipping or insufficient frequency information on the waveforms. So we also know that we're going to have to update these readings of frequency and V peak to peak every time step. So we know we're going to have to go into the time step event handler code, and we're going to have to make sure these are refreshed every time step. And we're going to have to do it for both channels if they're both selected. So let's take a look at the code that I've added in order to implement this. Right, so here we are on the code we've developed so far. Again, I encourage you to look at the previous videos to see how to get to this point. We've got our using statements, docs, to do, initializing, and then some existing code, and we've got the methods and event handlers. Now we said the first thing we're going to want to do is make sure that every time step we're going to update the V peak to peak and the frequency measurement. So every time step we're going to ask the scope, hey, what's the frequency and what's the V peak to peak of each channel, and then update. So what we'll do is we'll go into the event handlers, and down here is the big workhorse, which is the timer tick event handler. For the waveform capture every 0.2 of a second, it's going to go in here and it's going to update stuff. So as we had before, if we're in sweep frequency response analysis mode, this scan will be true, but we're not going to look at that now. We're going to be in waveform mode. So we'll scroll down here and we have the else if we're in waveform mode. Here's the code we're going to use with the addition of the measurement capability. So if we're in waveform mode, if channel 1 is checked, is true, and channel 2 is not checked, it's false, then we're going to say, okay, I just need to capture waveform 1 and measure waveform channel 1. So I'm going to clear all of the data points in series 2, which is channel 2, to erase that from the chart. Then we're going to capture scope waveform as we had before, and we're going to give it channel 1. And then we're adding this measure scope waveform method, and we're going to tell it channel 1. So it's going to go through and it's going to query the scope, ask it what is the V peak to peak in frequency for channel 1. After that, it's just going to make those frequency and V peak to peak labels visible or invisible. If it's channel 1 selected, it will make the channel 1 labels visible, and it will make channel 2 labels invisible. So that's basically it. We're just, in each time step, if we're in waveform mode, we're capturing the waveform and then plotting it to the chart and then measuring by asking the scope what are the measurements. Now, if the opposite is true, if channel 2 is enabled and channel 1 is not checked, then we're going to clear channel 1 points, and then we're going to capture scope waveform for channel 2, and then we're going to add this measure scope waveform for channel 2, and then make the labels for channel 2 visible and channel 1 invisible. Else, if both of these are checked, we want to see both waveforms, then each time step we're going to clear series 1 points and series 2 points, and then replot them. So we're going to capture waveform channel 1, capture waveform channel 2, and then measure scope waveform channel 1 and measure scope waveform channel 2, and then make all of these visible since they're both checked. And if nothing's checked, we're just going to clear all the points. So that's basically it. So now we got to look at this measure scope waveform, which takes the channel number, and it's going to ask the oscilloscope what are the measurements, and it's going to put it in those labels. So let's go to measure scope waveform. So here we are in our methods. We're gathering quite a few methods. We've got about 20 methods now. We might want to clean that up. So here we are in measure scope waveform, private void, and it takes a channel number, an integer. We're going to have some doubles, which is the frequency that we parse. When we ask the scope what's the frequency, we're going to convert it into a double, and that's going to be freak. And same thing for V peak to peak. And then we're going to have this frequency string, which we're going to be using when we determine whether it's hertz or kilohertz or megahertz, right? So these variables, the first thing we're going to do is measure frequency. And as before, we're going to use this mbsession.rawio.write, replace common escape sequences. And if we look in the programming guide to measure frequency of channel 1, we do :measure :item with a question mark, which is very important. It's asking, it's trying to read the frequency. And then we do frequency, and that's what we want to measure. And the channel is channel. And what I'm doing is I am taking the channel number that we fed into this. It's an integer. And to make it a little bit easier, I am converting that to a string and appending it to our command. So no matter what the channel number is, it will give us the correct command to measure that channel's frequency. So we do the rawio.write, and then we read rawio.read for MB session, and that will give us what we normally get when you do a read, which is a byte array, and I'm going to call it freak bytes. And then we're going to encode that as a string using this encoding default get string, and we're going to feed it this byte array called freak bytes, and that's going to be the string representing the scientific notation of the frequency in string format. And then we're going to do a try parse where we feed it that string with the frequency. And as we've done before, numberstyles.ne, culture.info.invariant culture, and it will give us out a frequency value called freak, and that's going to be a double. So now we've got this freak is a double relating to the frequency. So now here is our logic that determines the applicable frequency units, either hertz, kilohertz, or megahertz. So we're going to say if frequency, measured frequency, is less than or equal to 999, we're just going to print it out as hertz. If it's 999 up to 999,999, just below 1 million, we're going to make it frequency, we're going to divide it by 1,000 and call it kilohertz. if the frequency is greater than 999,999 and below 999,999,999, we're going to call it megahertz, and we're going to divide it by 1 million, all right? So that's just to make things cleaner. You don't need this, but if you wanted to read out in hertz, kilohertz, or megahertz. Now, if we get a reading that is way out, if it's a bad reading, we're going to, for example, if we don't have enough data to measure frequency, we're just going to say frequency is 0 and the frequency string is null. So hertz, kilohertz, megahertz, or null. So now that we know what the frequency is and we have a correct hertz, kilohertz, or megahertz, all we have to do is fill out the labels with the correct frequency value. So if channel 1 is selected, I'm going to go to label channel 1 frequency, which is the label with channel 1 frequency, and we're going to print channel 1 frequency equals, and then convert the frequency value to string, and we're going to use this N2, which is numerical with 2 decimal points. So we're going to use frequency to string with an N2, and then apply the hertz, kilohertz, or megahertz string that we made up here, and that's it. However, if it's channel 2, we'll do the exact same thing, except the channel 2 label, and we'll say channel 2 frequency is whatever the frequency is, and the frequency string, all right? So here we've done the frequency, and we're all set. Now we can do the V peak to peak. So again, exact same thing, but the command is going to be a little bit different. We're going to say measure item question mark VPP, and that's actually what it's looking for to measure VPP. VPP in capitals, comma, channel plus the channel 2 string. So we send that out. Again, it comes back as a byte array. We convert that to a string, and then we take that and parse it, and we will get VPP, which is a double representing the actual peak-to-peak voltage. Now, if the V peak to peak is legit, I'm going to say if it's below 25 volts, it's legit. And then, as before, we say if channel 1 is selected, channel 1 VPP.text is channel 1 plus VPP equals plus VPP 2 string with the N2, and that's it. Else if channel 2, we go to the channel 2 label and fill that out. Now, if it's not a good reading, if it's outside the range of 25, then we're going to, if it's channel 1, we're going to say the channel 1 VPP text is channel 1 plus VPP equals asterisks. If it's channel 2, we'll do the same thing. Channel 2 is VPP equals asterisk. That's fairly simple code that will measure the scope values of V peak to peak and frequency. So now that's about it. We've got our application now that will measure both channels, or show you both channels, V peak to peak and frequency. And in the next video, I'm going to look at something really, really important, which is performance analysis. Now, we've talked before about timing. You know, how often can you capture? How often can you do a sweep frequency where you vary the signal generator and the scope? And there's a lot of detail in this performance. And what we're going to do is we're going to use some techniques to analyze how long each of these steps is taking to see what's slowing us down and if there's anything we can do to improve the response. So I encourage you to take a look at the previous videos and hang on for the next video. And if you like any of these videos, please hit the like button, subscribe, hit the bell notifications, and most of all, please let others know that we're here so we get some views. Really appreciate it. Otherwise, take care. Have a really good day. Thanks.